We started with simple models like logistic regression, linear regression. Let's say if I take a logistic regression, I can have variable x1, x2, x3, and so on xk, and I have the target variable y, and each one of them have beta coefficients. Here it can be called as weights as well. This is a logistic regression line. This kind of setup, these kind of models solve a typical type of problems which are relatively easy or which are having slightly lesser patterns. When the patterns are very much complex, when the patterns are non-linear in nature, then we will not be able to use a simple logistic regression line, which will give a linear decision boundary that can be used to separate only the classes which are very easily linearly separable. When there are non-linear decision boundaries, if this is the case, then we cannot use logistic regression. We may have to add one more layer in between. If we say this is input layer, if they say this is output layer, then in between we have to add what we have to add. We have to add a hidden layer with hidden nodes. If we add hidden layer with hidden nodes, let's h1, h2, h3, and so on hk, the number of hidden nodes depends on what is the complexity of the data. If the complexity of the data is really high, if there are so many intricate patterns, then we may need more hidden nodes. If the data is fairly straightforward, then we may need less hidden nodes. If you have input layer, hidden layer, and the output layer, that is known as an artificial neural network support. Okay, this artificial neural network system, if you have this model, then you can solve really complex problems, because every hidden node end up like a decision boundary. No matter how complex the patterns are, no matter how complex the patterns are, you can keep on adding these decision boundaries. Multiple decision boundaries put together will do the final classification very easily. Until now, we discussed only artificial neural network with single hidden layer. If we have multiple hidden layers, then such kind of artificial neural network is known as deep neural network. What is a deep neural network? If you have a single hidden layer, that is known as a shallow neural network. If you have multiple hidden layers, that is known as deep neural network. Now, the subject, the topic that deals with deep neural networks, which means with multiple hidden layers. That means between input layer and output layer, there will be multiple hidden layers or multiple types of layers. Definitely, artificial neural network itself is very powerful. That will solve a lot of problems. Deep neural networks is even more powerful. That is the reason why, because of the applications and all that, we are treating now this as a different subject. The topic that deals with deep neural networks is deep learning. So you can understand deep learning as a subset of machine learning. You take one of the algorithm of machine learning, which is ANN, you develop it further, that becomes deep neural network, and the subject revolving around deep neural networks is deep learning. One of the algorithms of the deep learning or deep neural networks is convolution neural network. Let us see what is convolution neural network. Today's program will be totally dedicated to convolution neural networks. Let us see what are these. Before I get started with today's program, are there any general questions that you have? Please let me know if anyone has any questions. Okay then. So are we ready to get started with this program for today? Convolution neural network, all of you. Okay, perfect. Let's go ahead. This session is getting recorded. It will be shared to you. So if at any case, if you want to recap ANN also, ANN session was already recorded. You may want to see that again, okay, before you watch this video. Okay. Convolution neural network. The applications of convolution neural network are computer vision. Whenever you hear about computer vision, whenever you hear about image processing using deep learning, now this is a self-driving car. From the camera of self-driving car, this is how it will see. It will take this as input and will say that this is all road, this is a car, this is a car, this is building, This is sky. This is classified as sky. These are classified as trees. These are classified as trees. This one is a small building, was a cement pole or something. Though it is a cycle, it has been classified as car. There is a person here. There is some grass. Okay, like this. There are all predicted values. Based on this prediction, the car will go in the direction where there is a maximum chance for the road. Whenever you hear about computer vision, whenever you hear about taking images or videos as input, using deep learning to solve the problem of computer vision, or doing the object classification, face detection, image classification, anything related to computer vision, anything related to image processing, video analytics, the algorithm behind the scenes is convolution neural network. It will use certain novel ideas to understand the images. It will use certain ideas to do the image processing. This can be, the application can be as complex as this or as simple as this. Somebody used CNN to do the cucumber classification. So there are multiple types of cucumbers. Basically, his grandmother produces all these, like she cultivates all these cucumbers and all that. So what he has to do is, a person has taken all these cucumbers. Earlier they used to do manually classification. This is rank BS, this is rank BL, this is rank M, rank M, rank BS. So they want to do the cucumber classification. They trained the model on this data, and CNN can be used even in doing this cucumber classification. This is an ad, by the way. I'll show you the actual video right after this ad. Yeah. So basically, somebody is using this. They'll say this is AI. Basically, when somebody says AI, they mean to say either machine learning or deep learning algorithm being used. Okay. So people used to work long hours for doing this classification. So apparently he is the scientist who is automatically doing it with a certain percentage of accuracy. So the applications of computer vision can be as complex as self-driving car or as simple as this cucumber classification. Anyway, let us see how CNN uses these images data, and how does it do this image classification, face detection, video analytics. Okay, one of the biggest issues of ANN, we already used ANN for image classification. Do you remember it? If you remember, we have taken this data set of numbers. We have taken this data set of numbers. Then we discussed that a computer sees these numbers as pixel values. If it is a grayscale image, then the number would be between -1 to +1 every pixel. If it is a color image, then you will have height, you will have width of the image, and you will have these pixels. Every pixel will be RGB intensity. That means you'll have height, width, the shape of the image will be height, width, and 3 RGB image intensities. So every image, if you say image processing, it is not literally images, numerical data analysis only. The numerical data part of images is the pixel values. You take those pixel values and analyze those pixel values. Okay, this is how computers see the images. But if we use ANN, normal ANN, artificial neural network, for image processing, there is one big issue. What is that issue? In ANN, what we do is we take the image and we make it into a single dimensional. Let us suppose this is an image of 16 by 16. This is how the original image looks like. But what happens in ANN is, we take this image and we make it 1 by 256 like this. If you remember our data set in ANN, what we did was, we have some around 7,000 images or so. The columns are the pixels. All the columns are all the pixels. So we have around 256 pixels, isn't it? So what we did was, one image of 16 by 16 has been converted into one array of 1 by 256. This is called flattening of the images. If you flatten the images, then you will lose an important property of images called spatial dependence. What is spatial dependence? There is one basic property of images. What is that basic property? Pixels around this area are similar to each other. pixels around this area are similar to each other. Pixels around this area are similar to each other, isn't it? If you give me the pixels around this, I'll be able to predict what is this. Pixels around this area are similar. Pixels around this area are similar. There is some spatial dependence or local correlation. It is not like if you just convert this image and flatten it in one way. By looking at this, I can say this is an image of dog. By looking at this one array, I will not be able to say that what image it consists of. Even here also, by looking at this, I can say this is the image of 6. However, if you give me this flattened one array kind of thing, I will not be able to predict, or I will not be able to say what image is that. So images have spatial dependence, local correlation. They are related to each other. Images, these pixels are related to each other. Surrounding pixels are related to each other. But when we flatten it in while building ANN models, or if you are using ANN, standard ANN for handling images, we have to flatten it. If you flatten it, flattening means what? Let us suppose if you have 200 pixels here, 200 pixels here, we will flatten it 200 by 200, 1 by 200 by 200. Overall, it will be 1 by 40,000. That is how we are going to flatten it. Earlier, our image was 16 by 16. We flattened it, we made it 1 by 256 like this. If you flatten images like this, which is a requirement if you are using ANN, ANN cannot accept this two-dimensional kind of data. ANN as it is, it cannot accept these images as it is. Since we have to flatten it, if you flatten it, then you may lose the spatial dependence. Pixels around the eye are similar to each other. Pixels around the nose are similar to each other. Pixels around the ear are similar to each other. But all this will be lost. Now, CNN, convolution neural network, somehow keeps this spatial dependence using some method. Once we understand how this spatial dependency is kept intact, that is what makes this convolution neural network slightly different from artificial neural network. Both are neural networks only, but convolution neural network somehow smartly keeps this spatial dependence. By keeping this spatial dependence, we will be able to effectively do the object classification, face recognition, anything related to images, we can very easily do it. First of all, have you understood what is spatial dependence? What is local correlation in images? Have you got that idea, all of you? What is local correlation? Spatial dependence. Basically, images cannot be flattened simply. They have local correlation. Pixel values are similar to each other. Try to participate, everyone. Everyone try to answer this. Have you understood? Have you got the logic here? Yeah. Basically, it's a simple logic. What is it? Images have spatial dependence. That means what? They have nearby pixels are related to each other. We cannot simply flatten it. Yes. Now, how do you keep that spatial dependence? Because the spatial dependence will be lost if you flatten the images. So ANNs are powerful algorithms, no doubt. That is the story until now. ANNs are powerful algorithms, there is no doubt about it. But the only problem is the spatial dependence or spatial integrity is compromised. It is lost. We need an alternative to our fully connected ANN models. We need an alternative for this approach. What CNN does, it will try to take the sub-regions. In CNN, the major idea is instead of flattening the images, take the sub-regions from the image. Okay. Then use it for the analysis. Take the sub-regions as the input. CNN somehow not takes the complete single pixel values as input. It will take sub-regions on the image as an input. By taking the sub-regions, somehow you can keep the spatial dependence intact. Somehow we will keep this spatial dependency. Yes, we will give respect to local correlation. That is what the unique property of images. Images have spatial dependence. How CNN keeps this local correlation? How CNN keeps this interdependency of the pixels around a particular point using a particular concept called filter. CNN uses a concept called filter, or it is also known as kernel matrix. Kernel matrix. using this kernel matrix, or in simple terms in outside world it is known as filter. You know what, you, me, everyone over here already we used filters, but we don't know that it is related to CNN and all that. Everybody over here, if you have ever picked an image, if you ever edited an image, you might have already used filter. Have you seen any of the image applications apply this filter, that filter, filter 1, filter 2, filter 3, isn't it? Filter 4, filter 5, like that. There might be so many filters. Let us see the question from the chat window. I'm converting 16 by 16 image. Okay, 16 pixels, 16 into 1 by 256. I know that every 17th element will belong to the same column. Why don't we use this basic info to maintain spatial dependence? 17th element will belong to the same column in the sense. So you mean to say, can we give this 16 by 16 image as it is to the input to ANN? Is that what you're trying to say?
Not exactly. So
Hmm.
we have to give a linear array, right?
Correct.
In my linear array, so 16 elements will belong to each row, right? So first 16 will be first row,
So
second
overall
16,
pixels will be how many overall pixels?
256.
256. So 256 input variables will be there, isn't it?
Yes,
Each pixel will be an input variable in ANN.
yes,
So 256 input variables are there. Now tell me.
right. So from the 256,
Input
uh,
variables which are
right,
x1, x2, x3 and so on, x256.
right,
Correct. Yes.
exactly.
Right.
So X1,
Hmm.
X17,
Hmm.
then I think X34,
Correct.
and
Okay.
then
Hmm.
X51.
Hmm.
So every 17th element
Correct.
will correspond to the origin, to the same column in the original image, right?
Correct. Yeah.
So why don't we use that to maintain spatial
Right.
dependence?
So how do we give that to ANN then?
Uh,
Is there a way to pass on multiple variables put together in one information to ANN? Is there a way for that? Let's say in ANN, how does your ANN look right now? X1, X2, and so on. X256 will be there, right? 256
right.
nodes in the input layer. And we have added, let's say, 20 hidden nodes, then 10 output nodes are there. Now, how do we say that X1 and X17 are
Uh,
connected to one node only? Is there a way
can
in ANN, in the
we
standard
create,
ANN?
can we create a layer that a first layer that
Hmm.
says take
Hmm.
every 17th element, so
Hmm.
x1 x17, group
Okay.
these,
Hmm.
then take x2 x18 x
Hmm.
whatever,
Right.
and group these together.
But is there any setup already? That is not there.
Mm.
That kind of setup where you have this one and you spatial dependence, not just row wise dependence, isn't it? Or column wise dependence. Right
Sort of
now, you are
radial
keeping it
dependence,
only column wise. Yes or no?
right? We need something like
But
a radial dependence,
we need spatial dependence. This
right?
is
Right.
related to this one. That means, according to your logic, we have to say this is, let's say, x23. Okay, let us suppose.
Okay.
Then we have to say this is connected to this, this, this,
Right.
this, 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 right?
Exactly. So something like
And
a
this
coordination
element,
number.
what about this element? It is connected to all its radials. Yes or no?
Yes.
Somehow we have to do all this. Yes or no? It's not just
Yes.
column wise. Yeah, that
Yes.
is done
Yes.
using filter.
Okay.
Got it?
Yep.
What is a filter? It will take one element, somehow creep all the information. What did we discuss? We will try to take this sub-region information. It's not just about column wise, isn't it? Like this one will do it for one column, but I have to take one element and I have to do it for all the rows as well as columns nearby. How do you
Yep.
do that? Using a filter. Got it? How filter works is what we are going to discuss now. How filter works, let us suppose these are your pixels. Only 7 pixels are there. Just for our discussion sake, I am taking 7 pixels. Now, this is the original image, which is 7 cross 7. Now, this blue color one is my filter, which is also known as kernel matrix. On this kernel matrix, right now, the size of the kernel matrix is 3 cross 3. What this will ensure? This kernel matrix will be passed this way, everywhere. Kernel matrix or the filter will be working on the full image. it will gives rise to a new image. So what it will give, let us suppose this is our image. Just for the sake of simple explanation, I have taken simple pixel values. Otherwise, the pixel numbers would be between 0 and 255. Okay, just a second. Hmm. Okay, now check this out. This is the filter. How filter exactly works is you have the original image. You have the original image, which these are the pixel values. Okay. Now this is the kernel matrix or the filter. Filter values can be anything. The filter can hold any values. As of now, for simple example sake, I'm keeping everything 111. When you apply a filter on top of an image, the filter will move in this horizontal as well as vertical direction, and it will give you a resultant pixel value after applying a dot product. How a dot product is applied? What is a dot product? If you apply this on top of this, corresponding elements will be multiplied and the final multiplication will be summed up. So when you have everything 1 1 1 1 over here, if you do a simple dot product, then whatever is the summation of all the values will come here. So 1 into 1 plus 1 into 1 plus 1 into 1 plus 1 into 1 1 into 1 1 into 1 1 into 1. Tell me what is the result of the dot product, since there are 6 here, 6. What about the number here? For the number over there, you have to move the filter one stride here. Just move this one stride here. Tell me the number over here, all of you. If you move the filter on the image, what is the resultant pixel value after applying the dot
Five.
product? Yeah. Tell me that, put that in the chat window. How much is that? Everyone need to answer. Not single person. Everybody need to answer. Calculate it and tell me. Yeah. Agreed? Is this 5? Is this 5? How do you do that? You simply do the corresponding elements multiplication, finally add it. Tell me what is the next number. So that is 5. What is the next number? For the next number, you moved it one more stride and then you come over here. Tell me how much is that next number here, everybody. Everyone need to answer. Yeah, I'm not getting responses from some people. Yeah, try to participate, everybody. How much is the number here? Corresponding elements will be added, so this will be 4. What will be the number here? Tell me what will be the number here. For this, I have to move it slightly lower. Okay. And then get the number. Tell me what is the number over here. This element. This element. What is the number over here? Yeah. Is this 3? This is 3. Right. Like that, I'll move the filter on top of the image. This is the original image. This is the original input. This is the new image. New image after applying a filter. After applying a filter, what is filter ensuring? The information that is somewhat spatial, it will try to somehow tie up this one pixel value here, one pixel value here. It is not a single pixel value. It is a result of applying a filter. It is somehow mixing the information from its spatially related values and keeping the number over here. Every number over here is not a single pixel value. That is the result of some spatially connected values are giving as one pixel value. This is what a filter does. Filter tries to connect the values that are spatially dependent. So what is a filter? You have some values in the filter. When you apply a filter on top of the image, you will have this new image. This will be convoluted image. Convoluted image. Obviously, you cannot make sense out of this image using human eye. Using human eye, we can understand the input image, but convoluted image we may not be able to make sense. But however, we are doing something here. What are we doing? We are keeping it ready for analysis, for object detection. For rest of our analysis, we have this spatial dependence intact. Somehow this pixel which are connected, they are all given as one number. That is what the filter does, isn't it? Like the way that you are thinking, maybe somehow every 17th pixel, first pixel, 17th pixel, 35th pixel, I'll somehow connect it. That is only from the column point of view. From the row column, from the spatial point of view, if you apply a filter, somehow by taking this as input instead of this, we will be able to see that okay, this is not just a single pixel image, it is the result of a filter. And this is also known as kernel matrix, and you can have different values in this kernel matrix, not always simple one need not be the only thing. If you change the values of this kernel matrix, don't you think your your convoluted image, the resultant image will change, isn't it? If I have this kernel matrix, instead of that if I have 100, then this will be a resultant image which is slightly different. If I have, let's say, 000, then this will be a different kernel matrix. If I have this one, then this will be a different resultant image. By applying a different kernel matrix, we will get a different image, resultant image. Do you agree with that point? Or no matter what I apply, I'll get the same image? Obviously that will not happen, isn't it? Depending on the values of the kernel matrix, our resultant image will change. There are some kernel matrices that are there to enhance the intensities. There are some kernel matrices or filters, these are known as, that are there to make the image smooth. There are some kernel matrices that are there to make the image sharp. That means if you apply this kernel matrix, the image intensity will be enhanced. If you apply some other kernel matrix, then the image will be looking smoother. If you apply another kernel matrix, the image will look different. The image will look retro if you apply a different filter. The image will look in some other theme if you apply a different filter. The image will look black and white if you apply a different filter. If you change the values of this filter matrix, the result will obviously change. Earlier there was a 6 here, now there is a 3, because we have changed the values of the kernel matrix. You can have many filters. In fact, these convoluted images is our first layer actually. This is the input image. This is the input image, which is the original image. This is the convoluted image. Why are we taking convoluted images? Because we want to keep intact the spatial dependency. Different type of kernel matrices are there. There are some kernel matrices that are detecting curves. That means if you apply that kernel matrix, only curves in the input image will be highlighted, rest all will be suppressed. Everything else will be not visible, only curves will be highlighted. If you apply another kernel matrix, only circles will be highlighted. If you apply another kernel matrix, only sharp edges will be highlighted. If you apply another filter or kernel matrix, both are same, only straight lines will be highlighted. For example, if this is your input data, look at this all of you. If this is your input data, okay, 1036. If you apply this particular kernel matrix, which is 000111000, then what this will do is it will highlight only vertical lines. Okay, one, this has vertical line. It has two vertical lines, they will be highlighted, horizontal lines will be suppressed. It has one vertical line, three horizontal lines, they will be suppressed. Three horizontal lines, one larger vertical line, one smaller vertical line, they will be highlighted by applying this kernel matrix. Check this out. The result of this, apply this kernel matrix on top of this vertical line highlighted, two vertical lines highlighted, one vertical line. Can you make a guess? What if I want to highlight horizontal lines only? No horizontal lines, two horizontal lines, three horizontal lines, three horizontal lines. How do you think the kernel matrix will look like? Make a guess what it would be. Looking at this, can you intuitively think to highlight only horizontal lines, to suppress the vertical lines and the other corners and all that? What it will be? Think about it, all of you. How that it will look? Yeah, all of you. What will be the values in the matrix? Right now it is 010 010 010. This will highlight all the vertical lines. How will the kernel matrix, which is of the same shape, which is 3 by 3, how that will look like? Think about it, all of you. What do you think? Is it 111000000? Is it this one? Or you are nearby but not exactly same? How that will look like? It should be what? Should be 000111100. I mean, this also will do the job. The perfect one, the perfect one would be this one, isn't it? Do you agree with this point, all of you? Yeah, does it look like a matrix that will highlight all the horizontal lines? Yes, it is the matrix that will highlight all the horizontal lines. If you apply this, no horizontal lines, nothing highlighted. Two horizontal lines, two vertical lines suppressed. Vertical lines suppressed, 3 horizontal lines highlighted. Horizontal lines highlighted, vertical lines suppressed. By applying a particular kernel matrix, we will be highlighting a particular feature of the image. Remember this term, feature. Every image is made up of so many features. Images have circles, images have sharp edges, images have these angles, images have horizontal lines, images have vertical lines, images have right open curve, left open curve. All these kind of features will be there in every image. Looking at these features, you can do this image classification very easily. The features that you find in a cat, the features that you find in a car are very different. Maybe car is made up of all these sharp edges, all these things. Maybe cat is made up of different features. These features define an image. By applying a kernel matrix, you can highlight certain type of features. You can highlight the features by applying this kernel matrix. There are so many kernel matrix. There are so many filters that you can think of. There are filters for detecting curves. There are filters for detecting circles. That means if you change the values of this, circles will be highlighted. Like the way here with these values, vertical lines are highlighted. With these values, horizontal lines are highlighted. With a different value, with a different value, circles will be highlighted. With some other kernel matrix value, the sharp edges will be highlighted. So there are some kernel matrices that are there for detecting curves. There are some filters that are there for detecting circles. There are some filters that are detecting for sharp edges. There are some filters that are detecting straight lines. You know what? What is the most important note here? What is the most important note? We don't need to provide kernel matrix values manually. We don't need to provide the kernel matrix values manually. We don't need to put the filter values. It is humanly impossible to think about what are the features in this image and what matrix will detect what features. No, all that you need to do is you manually initialize with some random values. With some random weights you initialize based on the input data. These features will be learnt over the time. These features will be learnt while we are training. That is what the CNN algorithm will do it automatically. If your image has circles, you don't need to provide the kernel matrix to detect circles. You just need to put a filter that will finally transpire to circle detection matrix. If you have horizontal lines in your images, you don't need to provide the kernel matrix that will detect the horizontal lines. You just need to have another matrix in place. That means you just need to configure, like the way we used to configure number of hidden nodes. You mention the number of filters. Let us suppose if your image is made up of 10 features, you give 10 filters. Each filter will finally transpire to one of the feature detection matrix. We don't need to provide kernel matrix manually. All of you acknowledge this point. Do we need to provide these values while we are building the model, while we are doing this object recognition? Do I need to provide these kernel matrices by myself? Not required. Not required. We don't need to provide the kernel matrix manually. If we give kernel matrix with random values, but what you need to provide, how many kernel matrices? Let us suppose your image has 100 features. Okay, 100 features only there. If you have all these 100 features, that means your image is more made up of these small circles, lines, these kind of curves, these kind of curves. Your image is made up of all these things. Okay, but you have 100 features, but you gave only 10 filters. While you are building the model, you configured only with 10 filters. What will happen to your model finally? What will happen to your model if you gave only 10 filters, but you have actually 100 features? What your model end up like? We have a technical term for it. If I'm not building the model that need to be as much complex as it to be, it has to be, but I'm building a very simple model for a really complex data. What will happen to your model? Your model will overfit or underfit. If you're building a simple model, the actual model is complex. If that data is complex, you're building a simple model, you will have underfitting. If you're giving too many filters, then you may have overfitting. So you need to give number of filters. Look at this. Number of filters need to be given. The filter values need not be given. If we give kernel with random values, it will automatically detect features. All of you, once again, acknowledge this. It will automatically detect features. This is a major advantage of CNN algorithm. Okay. So we have the data, we apply the kernel matrix. The kernel matrix will be initialized with random values. Every kernel matrix will end up like one feature detection. If we give kernel matrix with random values, it will automatically detect features based on the data. If your data have curves, these left open curve, right open curve, then one of your kernel matrix will end up detecting this, one of your kernel matrix will end up detecting it. If your really data has these kind of lines, one of the filter will end up detecting this, one of the filter will end up detecting this. Only thing is, you have to give as many kernel matrices or as many filters as possible. That's the thing. So definitely you have low level features. Whenever you take an image, if you zoom in a lot, have you ever tried it? You take an image, if you keep on zooming to the maximum extent, then what you see at the very, very low level, you will see only all these basic geometrical shapes. Do you agree with that point? You have horizontal lines, you have vertical lines, maybe you have slight curves, isn't it? Or maybe this kind of curve, that kind of curve. Some of the features with human eye, we will not be able to make sense out of it, but the low level features are basic geometrical shapes. These kind of basic geometrical shapes. These are all the low level features, isn't it? The mid-level features are a combination of these low-level features. That means if you zoom out a little bit, if you zoom into a great extent to this car, you will see all these lines only. If you zoom out a little bit, then the combination of low-level features, they will start forming some kind of mid-level features. A combination of low-level features. Do you agree with this point? Think about it. If you zoom out a little bit, a combination of these will make some kind of shape. Maybe then you start looking at the wheels, then you may start looking at this one, this one, this one, like this. If you go further up, if you do further up, that means these are low level features, these are mid level features. What are mid level features? A combination of low level, a combination of mid level features will give us high level features. Then you start making sense. Finally a car will finally look like this, isn't it? Car shape will start coming out if you further zoom out. Maybe a cat shape will look very much different than a car shape, isn't it? Yes or no? The features, mid-level features put together will give us high-level features. So there are low-level features in the images which are basic shapes. A combination of them will give us mid-level features which are like kind of middle shape. High-level features are the overall shape of the object. These features, if we detect carefully, if we somehow detect these features, then our object recognition, object classification will be very easy. That is the secret. The major secret of convolution neural networks, the reason why it works perfectly for images is the reason is filter. Filter means what? Kernel matrix. There can be multiple filters. Obviously, one filter is not sufficient. You will apply this filter, it will detect this kind of edges. You will apply this filter, that will kind of detect this. This will detect this. This will detect all the circles. Horizontal lines will be detected by another feature. Vertical lines will be detected by another filter. Yeah, you apply multiple filters. This is the actual image. The convoluted image, we will not be able to make sense out of it with human eye. But however, analysis or final model will use all these results from the features. Some features will be highlighted by using some filters. That means if you take this original image, if you apply this filter, this is known as unweighted smoothing kernel. Basically, if you put all the ones, then if you apply that on the original image, then the image will look smoothened. Okay. If you apply this kind of kernel matrix, look at this, all of you. This is the smoothing kernel. If you apply this kernel, the original image will look slightly blurred here, like this. If you apply this kernel, the image will look sharper. Okay, the original image is this one. This will look little sharper when you apply this kernel. Okay, by applying different kernel, by the way, kernel means filter only, filter and kernel. By applying different kernel, the original image will look very differently. Since we are not doing this for fun, we want to do this for object recognition. This is like usually outside world, when you are doing image editing, you will be doing this for fun, isn't it? By applying a different filter, their image classification is not your final objective. You apply different filter, maybe when you apply some filters, you look the image looks very different, sometimes it looks cool, then we tend to upload it somewhere, isn't it? But that is not what we are doing here. By applying a filter, we want to highlight some features. Okay. I think all of you who have used either Instagram or even in your mobile, have you ever seen that it says filter below the image? As soon as you take that image, below it you apply a filter. Have you ever used a filter on the original image ever? You can make the image look like Amro, Rise, Hudson, or basically filter means what? You have this matrix with some pixel values. You push that on top of the image, it will move on top of the image, both rows and columns. It will give you a new convoluted image. Okay. This usually we apply filter for fun until now. But from here on, what we want to do, we don't want to apply a filter that will make this image look in this different formats. This is not what we are looking for right now. We want to apply a filter. Filter number one, I want to apply a filter that will highlight all the vertical lines. Okay. Suppress everything else. It should highlight all the vertical lines. That is feature one. I want to apply another filter that will highlight all the horizontal lines. Okay. All the horizontal lines. I want to apply another filter that will highlight all the curves or different type of curves. Okay. I want to apply another filter that will highlight all the circles. Like that, I want to put as many filters as possible. I want to learn all the features of an image. From all the images, we would like to learn all the features. You know what? Once you have the features, then the job is done. Once we have the features, by looking at these features, you can tell. Don't you think so? Cat has a very different features compared to a car, compared to a table. If you have three objects, you have to do object classification between cat, car, and table. Don't you think table has different features compared to a cat, which has very different features compared to a car? If I tell you all the features of a car, you will be finally able to easily tell that is a car. Based on these features, I can say that this is a car. Based on these features, I can say that this is a cat. So detecting these features is the important thing. How do you detect those features? By giving as many filters as possible. So the first layer, earlier until now we have input layer, X data. In the input layer, you have the image. You have the output layer. Output layer has the results. Okay. Until now, we have the hidden layer in ANN, but here the first layer in CNN is convolution layer. What happens in convolution layer? We apply kernel matrices on the input image. This is the input image. The resultant would be convoluted image. So the key, the heart of convolution neural network is kernel matrix. Once we understand kernel matrix, the rest of the algorithm, what is there? Once you detect all the features, you can apply any algorithm on top of it. You can add another hidden layer on top of it. Then you are through because features are detected. Then classification can be done very easily. But this kernel matrix is the one that has changed the whole course of image processing until now. We don't need to provide kernel matrix values manually. Once again, I want to highlight this point. You do not need to provide kernel matrix values manually. But what you need to provide? Tell me, what you need to provide? Yes, I agree that you don't need to provide these
Number
numbers.
of filters.
Number of filters, that is correct. You have to provide how many? How many kernel matrices should be there? That is in your hand. That means how complex or how simple your model is, that you need to configure. That is in your hand, that you have to configure it. You have to rightly configure it. Obviously we have to fine tune it. Maybe in one shot we will not get to know number of filters, number of kernels. You have to provide it. If you say 10 filters are there, 10 kernels are there, 10 features will be learned. If you say 50 filters, 50 features are there, 50 filters will be learned. In fact, we are going to see a way how to fine tune it, how to give these numbers carefully, how to draw or create a perfect CNN architecture in some time. Okay. If we give kernel with random values, it will automatically detect features based on the data. So what happens in the convolution layer? What happens? We take the original image, a particular feature will be highlighted. Maybe with a human eye, you will not be able to detect. Though for the example sake, I'm saying that some of them will be highlighting circles, some of them will be highlighting straight lines, some of them will be doing this, doing that. Just for the example sake, I am discussing. But with a human eye, one cannot really see what a filter is doing. One cannot really see the resultant convoluted image and say that, you know what, only this thing is highlighted here. Some of the images are beyond human imagination, isn't it? We cannot look at everything and make sense out of it. However, some features that are present in each image are learnt using this kernel matrices. Let us suppose if I take the image of this cat, if I apply a particular kernel matrix, I'm just thinking it may be highlighting this overall outer shape of the cat. If I apply another kernel matrix, if I apply another filter, I'm thinking that it is highlighting only this part of the cat. Obviously, these features are not found inside a table. Inside a table, you will never have this. In a table, you may not have this. In a table, you may have a different type of feature. Then when you are distinguishing table versus cat, you can very easily say that, okay, this feature contained by cat, this feature can be seen in cat, this feature can be seen in cat, it cannot be seen in a table. Finally, the model will learn that over a period of time by looking at multiple cats. Next time when the new feature like this comes, then it will see that, okay, this feature, I can classify this as a cat now. Okay. So the convoluted features, or the features in short, are very much important. Okay. They are gathered, or they are found over a period of time by giving as many images as possible. Obviously, I have to give thousands and thousands of images of cat for my algorithm to learn that this feature is a repeated feature inside a cat. There is no such feature inside a table, isn't it? Obviously, I cannot just give one image and ask the algorithm to learn the feature. So let us see one example how it happens, just for the sake of understanding how convolution works. Okay, you take this original image, which is 35605360 by 3. All of you, let us open the code file. The code file can be found in the class Google Classroom. Either you open this from Google Classroom, or directly I'm typing this in the chat window. You can open it from the chat window as well. Okay, this link location. Otherwise, you know how to open it, isn't it? You have to go to Google Classroom and then CNN and all that. Import the packages. Either you can create a copy of this and change it, or you can execute without any addition. This is the original image of a cat. This is the original image of a cat, which is 3560 pixels in height, which has 5360 pixels in width. Number 3, can somebody tell me what is 3 here? Pixels in rows, pixels in columns is fine. What is that 3 there? Do you remember it? We discussed it
Color.
already. Yeah, the color. Color is always given as RGB. 3 channels are there. Okay. So images have depth. Now what am I doing here? Con 2D. I'm applying convolution layer. Filters equal to 1. One filter of size 3 by 5 by 5 is I'm applying. I'm applying some random values in that filter. When I do this, when I apply this filter, and this is for actually drawing the image. Generally, we don't draw it. Just for the sake of looking at the result, I'm drawing this. So let us see how does the resultant image looks like. Okay, when I apply some random values on top of the convoluted image. All of you can do it along with me. Yeah. So this is the image after applying the filter. I have applied one filter. Since we are working with random values, maybe your resultant image may not be same as my resultant image. Here, specific features are highlighted. Maybe I'm thinking white is highlighted, or a typical color is highlighted, or some pink color kind of thing. Like eyes are highlighted here of the, and little bit of nose, little bit of ears are highlighted. Obviously, if I change the filter, that means if I change those random values, right now kernel initializer is random. If I change those random values, something else is highlighted. Whatever was highlighted earlier, this is not the same thing here. If I change again, something else will be highlighted. Okay, it depends on what are the values of that filter. Check this out. Have you seen different filters will learn different features? Different features make, all these features will make the overall image of a cat or a dog or whatever is the object that we are classifying. Okay, and obviously you can have multiple filters. It's not just single filter, you can have multiple filters. Okay, that is the first part. So the story so far is you have input layer, you have convolution layer. Inside convolution layer, you have filter 1, filter 2, filter 3, filter 4. You can have multiple filters. Okay. I will pause here and take the questions.
So we got the that in the model summary we got uh, output shape as 3556 5356. So how did we get that? It's like how that number we got.
So the original input image is 3560, right?
Yes.
5360. So if you apply a 5 cross 5 filter, if you apply a 5 cross 5 filter, it will be from here to here, it will be applied, and from here to here, yes or no?
Yes.
So on the edges, 4 pixels will be gone here, 4 pixels will be gone. Overall, I think around 8 pixels will be gone. That is what, like 4 pixels there, 4 pixels there, 3556. That is like from 3560, 2 pixels over there because it is a 5 cross 5 filter. So if we apply a 3 cross 3 filter in the example, if you see, in our example, we applied a 3 cross 3 filter, isn't it?
Yes.
On a 7 cross 7 image, 7, 1, 2, 3, 4, 5, 6, 7. So this is first result, that will give 6, 2, 3, and so on until here you will be able to come. Then we will stop. That means 1 pixel will be lost here, 1 pixel will be lost here. A 7 cross 7 image applied a 3 cross 3 filter will give you a result of 5 cross 5. Similarly, if you apply 5 cross 5 on top of it, you will lose 2 pixels here, 2 pixels here. So overall 4 pixels will be lost. Same thing is the case with the rows as well. Okay.
So and one more thing is
Here,
like in
so there are 3560, 4 pixels are lost. 5360, 4 pixels are lost. Yeah, please go ahead.
then one more thing in ANNV there was a in node called bias. It's like for every
Hmm.
hidden layer it provides the bias. So in
Good.
here in CNN, where
Also,
is
there
there
is
any
a
bias?
bias. Yes, there is a bias even in CNN. So right now, this filter, which is of the shape 3 cross 3 here. Okay. So usually we will say 9 weights, right? 9 weights. 9 weights plus 1 bias will be there. So overall, there will be 10 weights here. So these are the weights that will be finally found. Right now, we are starting with random values. This each one of them will end up like a filter deduction. So these numbers, depending on what features that we have, all of these filter values will be ending up with some standard values which will be detecting a particular feature. There will be a bias term here as well. Can we use this filter to understand how a snake or other animal would see an object? Not sure. This is what are we doing here? There is an image, input image, right? We want to classify that image. Let's say given this image, whether this is a cat, or given this image, whether this is a car, given this image, whether this is a tree, given this image, whether this is a, you know, what do you call, building. What we are doing here, we are trying to identify all the features that will make a cat, image related features, all the features that will make a building, all the features of a tree, all the features of a car. We are capturing all those features in convolution layer. Once all these features are captured, then my classification would be easy. Okay. Next time when you give a car image, automatically I will tick all the features that made up a car, then I would predict that as car. That's what we are doing. We are not really finding how other animals will see the rest of the world. That research is a totally different thing. Yes, we are getting some convoluted images, but that has no connection to how other animals perceive the input data. Right, the story so far is you have input layer. In the input layer you have input images, isn't it? In the convolution layer you have convoluted images. Features are found here. Yeah, somebody was trying to ask a question. Please go ahead. The only issue with convolution layer is looks like there is a lot of duplication. Have you seen that? Have you paid some attention to this duplication? Because we apply a filter. When we apply a filter in the resultant image, what happens is, look at this. Let us see one of the result of the filter. Yeah, check this out. When you apply this filter on top of the image, this 6 will also contain this portion of the data. This 5 will contain this portion of the data. The next one, there is a lot of duplication. Duplication in the sense, same information is considered multiple times. This 6 also has the similar information. The 5 also has a similar information. 4 also has a similar information. There is a lot of duplication of information. Have you observed it, all of you? Like when we are applying filters, when we are moving it row wise, column wise, here this information is again considered in the next pixel as well. This 3 contains a lot of info from 6. This 5 contains a lot of info from 6. This 4 contains a lot of info from 5. This 3 contains a lot of info from 3. There is a lot of duplication of information. That is why the next stage, what we do is something called down sampling, which doesn't really hurt our overall analysis. What is down sampling? Simply reducing the size of the resultant of the convolution images. Down sampling layer is also known as pooling layer. In the pooling layer, only size of the image reduces to almost half. If the original image is having 1500 or 1600 by 1600 size, then after applying pooling layer, you will have image 800 by 800, almost halved. Strictly speaking, it is almost 1/4, isn't it? Like square wise, you will lose 800, half in rows, half in columns. How applying a pooling layer works? Let us suppose if you have this as the original image, we say max pooling 2 cross 2, 2 cross 2 matrix, max pooling. Then what will be the result? We will take a 2 cross 2 matrix on the convoluted image. This is the convoluted image. And we have this 2 cross 2 matrix, whatever is the larger value in this 2 cross 2 matrix, 6 is the larger value. That only that number will be considered, remaining will be ignored. Next, we will move here, not with one stride, we will move 2 strides. That means we will ignore this part is not need to be done. We will come here 2 strides. 2 cross 2 matrix, what is the maximum number? What is the maximum number here? 5. You move here. What is the maximum number? What is the maximum number here? 6. When you move here, it is not possible, so ignore that. So you move here 3. You move here 3. You come here 6. That's it. The result of a 7 cross 7 matrix is now 2 cross 3, almost half, even less than half. If the matrix would have been 8 cross 8, then the output would have been 4 cross 4. Why we do this? Because there is a lot of duplication of information. We already know that a lot of information in 4 is there, in 5 is there, in 5. Like these are all very much having a lot of duplication of information. To keep our calculations at a lower value or to somehow execute much faster, what we can do is max pooling with 2 cross 2 matrix of straight 2. Or else we can do average pooling as well. Max pooling is one type of pooling, or average pooling is taking all these values, taking the average of them, taking all these 4 values, taking the average of them. In a matrix earlier we used to take max value. Instead you can take the average value. So that is the second layer in pooling. What happens in pooling layer? Most importantly, what happens? Tell me all of you, have you realized it? In the pooling layer, the size of the input image would be reduced. By reducing the size of the image, we can actually make the calculations faster. Otherwise, this image processing will take a lot of time. In the pooling layer, downsampling of the data happens. Okay. How many parameters are there in the pooling layer? There are no parameter. It's a simple downsampling. Pooling is like a more like a practical, trick that we use to execute the algorithms much faster. This is what the result of the convolution layer. In the pooling layer, when you apply pooling layer on top of the resultant convolution layer, let us see how does the output look like. The output looks almost the same. The output doesn't change. Can somebody tell me what has changed in pooling layer? What is strikingly different here?
dimensions of the image.
The dimensions. Yeah, original image shape is how much? Original image shape is 3560 53603. Ideally, I should have been taking this image for image classification later on. That means I have to say based on these features whether this image is cat, or based on these features this image is car or something. But I am reducing this image. Check this out. Even if you see original image or reduced dimension image, to a human eye, it doesn't look very different. However, the number of rows, number of columns almost half. The image is 1/4 size right now. If you consider this original image, which is of the size 3560 5360, the new image is half the rows and half the columns only. Dimensions have almost reduced to half. This is very much important when you are actually doing these practical problems with so many images. We have to make sure that we are keeping it at a lower value. So in the pooling layer, the size of the image reduces to half. One of the important thing that we need to focus on here is original image has a size of 5360. Now it will be somewhere around 25. 3560, it will be somewhere around 1600 or 1700. So the story so far, you have the input layer which has input images. Convolution layer, which is the key factor. The name convolution neural network is itself is coming from the fact that you have the convolution layer. This is where filters are applied. This is where you will have multiple features that are detected. Remember, multiple filters are applied here, not just single filter. In our example, I said number of filters equal to 1 only, but later on we will be giving multiple filters. Yeah. Even color channel will be lost even in the convolution itself. If you look at the convolution, there itself the color channel will be lost. Check this out. When you apply convolution, there itself, through the depth of the color you will go, and that will be one will be the output. Okay. After that, if you apply filter, it will be same like from the rows and columns, it will be halved. Okay. After that, you apply pooling convolution layer. You have multiple filters which will detect multiple features. Then you apply pooling layer. After pooling layer, what happens? Give me an idea. You have input images. You have input images. You detected all the features. You detected all the features now in each of the image. Finally, at the end of the day, you have to do the classification. Now you have the features. Instead of taking the input data, now I have the features. For doing the classification, usually what we use? Usually what we use for doing the classification? We use ANN.
Data and
So what we can do is we take all these features and then we try to build an ANN model on top of it. ANN has three layers: input layer, hidden layer, output layer. The only problem with input layer in ANN is we used to flatten the data, but that we did not like it. Now that you captured all the features, we created convolution layer by adding all the filters. Now we downsampled with pooling layer. Now that you learned all the features, you can very much safely flatten it. Flattening means what? Now you can somehow build an ANN on top of it, no problem. Input layer, hidden layer, output layer is the structure of ANN, standard ANN. Input layer followed by what? Tell me. Input layer. First one is input layer. I'm talking about the CNN. Input layer followed
convolution,
by convolution layer
max
followed
pooling,
by which layer?
max pooling,
Pooling
pooling.
layer.
pooling image.
Usually convolution layer, pooling layer. Let's say this convolution layer is detecting low level features. Then you apply pooling. To detect mid level features, again convolution layer and pooling layer. To detect high level features, again convolution layer, pooling layer. Like this is a combination of input data, this is a combination of low level, this is a combination of mid level. Then finally what we do is we flatten it, or
Flatten.
we add the hidden layer. So you have the hidden layer, fully connected hidden layer. You can now connect it to output layer, no problem. Now that you have learned all the features of the images, earlier taking the image itself and flattening it is not a good idea. Now that you learned all the features to do the object classification, image classification, you can add the fully connected hidden layer. CNN architecture is input layer followed by conv layer followed by pooling layer. Usually again we add another conv layer, another pooling layer, another conv layer, another pooling layer, depending on the complexity of the data. Finally, just before the output layer, what will output layer has? Output layer has output classes. How many distinct classes are there in your output? Those many classes will be there in the output layer. Just before that, you add the fully connected hidden layer. Fully connected hidden layers are known as dense layers. Densely connected or fully connected. Add the dense layer, then you are through. So what we do is we take the input image, we add convolution layer. Okay. In the convolution layer, you can have multiple filters. Again, we add a pooling layer. Usually pooling layer is not shown in the diagram because it's a complex diagram. Add another convolution layer with multiple filters in it. This is a convolution layer which will learn all the low level features, mid level features, and high level features. Then on top of it, this is the fully connected hidden layer. Then you have the final output layer with how many ever output nodes are there. This is the theory of CNN. Obviously, we are going to do one or two case studies. Before that, it's a good idea to get an idea on what is happening inside a CNN model. Now we will take one small case study, one simple case study. Later on, we move on to one real application of CNN. There is a data set called CFAR10 dataset, which contains 60,000 images of size 32 by 32, which is color. 32 by 32 color means what? The original shape will be what? 32 by 32 by what?
3.
3, because you have color, which is another dimension. So you have around 10,000 images. You have 6,000 images of aeroplanes, 6,000 images of cars, birds, cats, deers, dogs, frogs, horses, ships, trucks. We have to build a CNN model. Given any new image, first we have to build the model on top of this data, learn the patterns. Given any new image, the model has to predict what is the given image. So how do you build a CNN model for this? First of all, let us get the input data. This data set is already present in TensorFlow and Keras. Okay. TensorFlow, what is TensorFlow? It is the Google's version of deep learning framework or the package. So we are using TensorFlow. Out of that, Keras is a sub package. So we are using Keras datasets to get all the data. This particular step will get the data. We can print few of the records and check few of the images. Downloaded the data. Here are some of the images. Obviously 32 by 32 means very, very small pixelated images. Later on we'll take larger images, but still we'll be able to make a sense out of it. Like see this frog, truck, deer, automobile, cat, ship. It's always a good idea to take large images, but on the flip side, if you take large image, your computation will take a lot of time, and sometimes our system may give up also. So that is why if we will try to take as small as images as possible, which are still not really losing the key information, which can be still used for your object detection. These are some sample images. Overall, we have 10 classes in the output. If we are building a CNN model for this, what should be the approach? Okay. So usually the structure of CNN model is like this. Look at this, all of you. You first add, you have input layer. Usually we don't give info about input layer, isn't it? We directly give the info about the first hidden layer. So you have the input layer, and then after that you add the convolution layer. So usually what we do is we add convolution layer 1 with many filters. Okay. After that we add a pooling layer. This is known as Convolution layer to detect low level features. Tell me an example of low level features, anybody. What could be low level features in any image? These low level features are typically same for all the images. Give me some examples of low level features. That means when you really get into deep inside any image, that means if you zoom in a
Lines,
lot, okay,
circles,
small lines, small structures, okay, these are all the low level features, okay. Yeah, horizontal lines, vertical lines. Usually these low level features are less number. No matter what image you take, think about it, no matter what image you take in this world, if you zoom in a lot, you will find basic geometrical shapes only, isn't it? So you can give the number of filters in convolution layer 1, you can keep it like 8 or 16 depending on the data. Then you add one more convolution layer. You have convolution layer 2 with how many filters? A combination of low level features will make mid level features. These are mid level features. After that you add pooling anyway. Mid level features, let us suppose if I have given 16 filters here, 16 features at the low level. What should be high level? High level is what should be here? It is mid level, slightly higher than the low level. Mid level features are a combination of low level features. They are a combination of low level features. What should be that number? Higher than 16 or lower than 16?
higher,
Combination of, yeah, don't you think
higher.
so? Yeah, the combinations will be more than the previous ones. Think about it, all of you. Shall I give 8 here? Shall I give 32 here? Double or half? Mid-level filters
32.
should be double than that or half the previous ones. Double, isn't it? Because the combinations can be much more. Okay, so mid-level features are 32, a combination of low level features. Then you will have another convolution layer 3 followed by pooling layer. Then I have to give how many filters here? The high level features, these are high level features. These are a combination of mid level features. What should I give here? Yeah, shall I give again 16 here or 64 here? What should be this number? Yeah,
64.
this should be 64. Yeah, usually that is how you construct a convolution neural network. Here is the code. Models equal to model dot sequential. This is the code inside TensorFlow. The most important part you need to pay attention is convolution 2D 16 3 cross 3. Can somebody explain me what is this 16? What is this 3 cross 3?
3 cross 3 is the size of the filter,
Size of
and
the kernel
6
matrix or the size of the filter. Perfect. What is
and 16 is
16?
the number of filters.
Number of filters.
Filters.
In low level, let's call this one low level. Input shape equal to 32 by 32 by 3. Can somebody tell me what exactly is this one? Input shape.
Dimensions with correct RGB.
Input images are 32 by 32 by 3. Okay. Usually right after applying convolution layer, what do you apply? Usually right after convolution
Max
layer,
pooling.
yeah, you tend to add max pooling. This is the standard step. Max pooling 2 cross 2. Okay. After that, mid-level features. Now someone else try to explain this 32 3 cross 3. What does this mean? 32 comma 3 cross 3. What does this mean?
32 is number of filters
Number of
and
filters are 32. Why
and
32 after 16? Why 32? Once again, try to acknowledge this, all of you. Why 32 here? Is it a
because
random number that I'm picking or I'm going smartly here? Think about it, all of you.
since we are dealing with mid-level features, so we are
Mid-level features, which are a combination of low-level features. So we have to take more combos here. So 32, 3 cross 3 is the size. Usually the suggested size is either 3 cross 3 or 5 cross 5. Odd numbers are preferred. Then you have the max pooling. The last one. What about this one? The high-level features. From 32, you take 64 high-level features. Obviously, the same logic. The combination of these 32 filters would be even more. Combination means permutation combinations even more would be there. 64 3 cross 3 is the size of the filter. Once you have learned everything, now I'm perfect. Like I learned mid level, low level, high level. Now I'm very confident I can do the classification. That means my final layer has dense layer which has 10 classes. What are the 10 classes? Horses, you have these aeroplanes, you have these frogs, like the 10 classes are there. Before that, which layer we add? Before going from convolution to the final output layer, this is the
Flatten.
output layer. We flatten it and we add one more
Ends.
hidden layer. Tell me how many hidden nodes are we adding here in this hidden layer?
64.
64. That's what is usually the structure. Input layer followed by convolution pooling, another convolution pooling, finally connected and output. You know what? Sometimes you add two convolution layers for low level, two convolution layers for mid level, two convolution layers for high level. Because the data is so complex, the features are so many that you may need to add two, which is also possible. Here in our data set, one convolution layer at each level is sufficient. This is the model summary. You compile the output. Usually, these model building steps take a lot of time. You can use the option called model.save weights. That means if you have executed 10 epochs today, okay, tomorrow you want to like 10 iterations. Tomorrow you want to execute from the 11th iteration onwards. You can save the model. You can save the model. You can load the model, previous model. If you run two epochs on top of it, effectively we have executed two epochs here, and then we loaded the model, executed two more epochs. What does that mean? It means that we have effectively executed four epochs. The reason why I'm making you do this is some of your image processing examples may take a lot of time. To make sure that whatever we have executed, if we want to save it, we can save the weights. As a matter of fact, this example also takes a lot of time. So I have saved my uh, weights file. What you can do is you can download my weights file, and then using that weights file on top of it, you can execute two more epochs. This is what the result is. So the resultant is overall 70% accuracy on train and test. Usually the accuracy of the model depends on the input data.
Excuse me, sir.
Obviously, yeah,
Sir, can you please explain epochs part again? Sorry for disturbing.
yeah. So the epoch means like, do you remember back propagation in from ANN? The algorithm that we discussed in ANN, how do we solve the problem? We do the feed forward followed by error calculation, back propagation. We send the data forward, we calculate the error and do the back propagation. Then we update the weights, isn't it? While
Yeah,
finding
yes,
the
sir.
weights.
Yes, sir.
This is known as one epoch. At the end of one epoch, the weights will not be perfect, right? We start with random weights. Yes or no? We
Yes, sir.
start with random weights. Then at the end of one epoch, we have slightly better weights. At the end of one epoch, can I finalize the model, or I need to run for one more epoch? I need to keep on running this for multiple epochs, isn't it?
Yes, sir.
Yeah. So when the error is almost near to zero, or when the error cannot be reduced further, then we'll stop it. Okay. That is what an epoch means. What I'm saying is, let's say you have executed for 10 epochs. Okay. And you got an accuracy of, let's say, 70%. You realize that you can go up till 75% accuracy. That means when you re-execute it, the model will execute from again from the beginning, isn't it? When you re-execute it, let's say you have executed this model and you gave 10 epochs. What if I want to run for two more epochs? Then you can save this model. The current stage of the model, the current stage of the weights can be saved. That weights can be loaded. On top of it, you can run two more epochs. That means here I have executed two epochs. After that, I have loaded the model, ran two epochs. Though I gave two epochs here, effectively how many epochs this result is showing me final result?
Sir, 12.
If I would have saved the 10 model here, since
Yeah,
I
yes,
have
yes,
saved
yes.
2, so it will be 4
4,
here.
4, 2 plus 2.
Though it is saying epoch 1 out of 2, but is it really starting at random weights, or it is starting at the weights that were the result of the previous number of epoch? Since we said
Previous.
model.load weights previous, so that is what
Previous.
this load weights is doing. Okay.
Thank you, sir.
This is what the overall CNN simple model, but every year there is a competition that runs. The image recognition scientists around the world, they will be taking this dataset called ImageNet dataset, ImageNet project. It has 14 million images. 14 million images from 20,000 categories. Almost all the images that you see in day-to-day life, all the objects from balloons to strawberries to ships to monkeys, laptops, mobile phones, water bottles, pens, pencils, everything, windows, doors, routers, everything, tables, fans, all the items, okay, around 14 million images. What these scientists have to do is they have to build a CNN model with some more tricks and maybe adding few more things here and there, a little bit of parameters tuning, etc., etc. So there is a benchmark model that will have certain kind of accuracy. If the new model beats that, existing model in terms of accuracy or in terms of speed, then that model will be given a prize, or it will be declared as this year's best model is this one, okay, like that every year some. So AlexNet is one of the CNN architecture which is very famous. It has solved that ImageNet project effectively, okay. So almost it has given, it has shown a lot of improvement, almost 90% accuracy it has given. It was built by Jeffrey Hinton, Elias Sutwaker, Alex Krzyzewski. Jeffrey Hinton is known as father of deep learning. He works for Google. He's the one who created a lot of deep learning algorithms and a lot of deep learning parameters. Okay, the term deep learning itself is given by Jeffrey Hinton. So these guys have created one model. If you look at the architecture of that model, input data has 224 by 224 by 3. Size of the input data is 224 by 224 by 3. By 3 means what? That color images. So they have applied 96 filters in CNN1. Then they applied 256 filters. Do you remember it? What did we say? When you go to next layer, usually we tend to almost double it. 256 filters in Conv2, 384 filters in Conv3. So by now you have low level features, mid level features, and then for high level features, again they applied 384 and 256. This is supposed to be one of the most complicated network. Again, on top of it, dense 4096. Can somebody tell me what is this? Again, dense 4096. What does this mean?
Number of hidden layers in
Number layers or
nodes,
nodes?
nodes,
Two
nodes.
layers are there with 404096 nodes. Like this, they have created this network. Okay. In fact, such kind of networks are known as pre-trained models. What if that network is publicly available? Can we use it? Like the way we can load the weights, right? Load the weights and use it as if we have built that model. Like that, there are some pre-trained models that are available in Keras. We don't need to build the model from the scratch. If you have an idea in your mind, using image processing, I can solve this problem. If something is, an idea is coming to your mind right now, you don't need to really take a lot of images. You need not train it. Already somebody has trained it. If one of these models is solving that purpose, directly you can build an app on top of it. You don't need to really train the model on your data. Given that your idea has related data to this. VGG16 is a pre-trained model. You can load it, you can load the weights, you can load the weights, you can use for your prediction. Inception V3 is a pre-trained model. You can load the weights, you can use it for your purpose. ResNet 50 is a pre-trained model. You can load the weights, you can use it. Exception is another model. These are all model names, pre-trained models. Let us see one such example. So here is one model called ResNet. That is a model that was already built. I'm simply loading it. I'm writing one line, my model equal to ResNet 50. Just get all the weights. That is it. Model building done. It's not model building. It is model copying from someone else. Now I have some images, sample images. You can try image number 1, 2, 3. Then the predictions will be given to you. So this is the image that was given. The output was predicted as mousetrap, hamster, weasel. Different type of categories of mouse, rats. If you give image number 1, you can also make the changes here. If you give image number 1.jpg, this is predicted as African elephant, tusker, and Indian elephant. If you give image number 3, 3 is rat itself. Maybe give image number 2, 2.jpg. Are you getting where I'm making the change? Image name equal to there. It is predicted as Macau Patas Guan. I thought why it is not simple monkey. Apparently these are different types of monkeys. It is predicted as already monkey. Around this, you can build an application. Already you have the solution in front of you. What if you want to provide a solution? Let's say you can find where the elephant is. Okay. Maybe for the forest department, you can create an app. Okay. These forest rangers, they don't need to manually do this monitoring of elephants. You just put the cameras at multiple places in the forest, and these cameras will keep on taking the images. As soon as you find elephant, as soon as you see the output is African elephant or tusker or Indian elephant, then you can take this output and raise an alert system or something. You can see the elephant here, something like that. Are you getting it, what I'm trying to say? The output is, our analysis stops here. How do you build an application on top of it? That is creative. Where are you using this image processing? That requires a creative idea. Where can I use this? Maybe you have rats. Okay. Maybe once you can predict what is a rat, maybe large godowns will be there, large warehouses will be there. There, finding out rats can create a huge havoc. Once you find a rat, automatically you can raise an alarm or something to capture it, or something to make it, or once it enters a particular region which it should not enter, you can somehow predict all this, capture all this. But this is a pre-built model. The only rule would be the images that they have trained on, only those images it will accurately predict, otherwise it will fail. That is the power of CNN, where it can be used for image processing. Yeah.
So what is that 0.94 after that each thing? So
The
is that the
probability, the
okay, go ahead.
probability that this much is for being a mousetrap, this much is for being a hamster and all.
Okay.
Yeah. Now what we will do is we will do a final project. Before we close this, we want to see the real power of CNN. Okay. Here is the data set where I have 27,558 images. Okay. I have two types of images: uninfected cell images, infected cell images. Basically, in Africa, malaria is a very big issue. In some countries, malaria here also big issue, but there very frequently there are a lot of serious cases of malaria. Now, if you do a normal malaria diagnosis, that means if you go to normal testing center, it may take a lot of time to determine whether it is a malaria or not. They use some precipitation technique or something, centrifugal or something that they will use. They'll finally tell you on based on the blood, they'll tell you whether you are infected with malaria or not. What if we take blood cell images? I take all the malaria patients, their blood cell images under the microscope, images. What if we take all the patients, all the normal healthy patients where they do not have malaria, these blood cell images, okay, maybe 10,000 such images, another 10,000 such images of healthy people without malaria. Maybe I can build a CNN model that will understand the patterns related to malaria cells, non-malaria. Next time when I give a normal blood cell image, that means the patient has to, like, there will be a kind of ATM like machine. One has to drop a small blood drop. Automatically blood cell images will be captured using microphone, this microscope. Then based on that, we can very easily tell within 2-3 minutes or within 2-3 seconds, using this CNN model, we will be very easily predicting whether there is any malaria or not. Okay. So that is the idea. Okay. Obviously we need the strong data set, perfect data set to detect whether there is any malaria or not. So here is the example. We luckily have the data set, malaria and non-malaria, from National Institute of Health malaria datasets repository. So here are some of the examples of infected cells. These are the images of the cells where malaria is there. These are the images of the cells where there is no malaria. So maybe next time when a blood drop is poured, as soon as the microscope takes all the images, if it sees these kind of features, then the prediction will be no malaria. If most of the cell images from one blood drop are like this, then there is malaria. Okay, so we can make this process very cheap. Once you have the model, then all that you need to build is what? Just a simple way of taking the images and getting the predictions. We can reduce the risk very much, and by diagnosing it very quickly, we can reduce the adverse effects of the malaria very easily. So we don't need really large testing centers or anything. We can simply have some ATMs kind of machines where people will get to know whether they have malaria or not. Okay, so this data of 27,558 images is what we are going to consider right now. Let us see this. Import the packages. Obviously this data is a large data set. I have kept it on Google Drive. To download it from Google Drive, we have to give the authentication. All of you click on it. You need to give the authentication, choose your ID, get the you click on allow, get this code, put the code here and click enter. After putting the code, you click enter, then your files will be downloaded. On the left side you see this menu item called files. These files will be downloaded. Cell images.zip will be downloaded. It's a large file. I could not keep it on GitHub. I have to keep it on Google Drive. You'll be able to download all these image files in cell images.zip. Okay. After that, you unzip it. Once you unzip it, two folders will be present inside cell images. Inside cell images, you will see two folders: parasitized, uninfected. Parasitized, zero. Zero means infected ones. Uninfected, one. P is the first alphabet. That is why our class 0 would be parasitized or infected cells. Class 1 will be uninfected cells. Parasitized. Here are some of the sample images from the data which you can print and see. Some of the infected cells, some of the uninfected cells. These are the infected cell examples. These are some of the uninfected cell examples. Okay. Now, since we are considering original images, until now we have never done this. Until now we have taken the data from Keras, from other places in terms of numbers. Here is the first time where images are inputs and they have dimensions, 3 dimensions, 100 by 100 by 3 or something like that. Images are real images are inputs. So this each of them .png images are inputs. So when you are using images as inputs, you have to use a different package for handling them. So let us see what is that package. So here are some of the sample images. So we have to use a package called image data generator. Basically it will take the images, then the generate data from there, numerical data from there. So we use data gen. We are trying to standardize the width and height. Some images are having higher width, some images are having lower width. To keep all of them at the same size, overall you can take some number which is near to this. Overall 128 by 128 is width and height. Create the training data, create the test data. You can give what should be training data, what should be test data. Basically image data generator is required when you have images, original images as input. Now comes the model building. Can somebody explain me what is happening here in model building? Okay, one person in chat window tell me explain about the first convolution layer. First convolution layer. Kernel size, number of filters. What's happening in the first convolution layer? We are adding 8 filters, each of them with kernel size how much? Each of them with kernel size 3 cross 3. Okay. Input shape, width and height of the image cross 3. We will give input only for the first layer. Max pooling. Dropout is for avoiding overfitting, underfitting. That is a different layer that is added. We can remove that also, or to avoid overfitting, we can add a dropout layer. Few of the nodes will be dropped while building the model. Then we added another convolution layer with 16 filters. The reason why we took only 8 filters is looking at the data, I can get an idea that these are not typical normal objects. These are very simple objects. I thought 8 filters are sufficient in the lower level. Then I went for 16 filters. Then I went for 32 filters. Then I have flattened it, added 64 hidden nodes. Then finally the output. Okay. Overall 407,000 weights are there. 47,000 weights. Build the model, compile the model. Okay. It is saying something is deprecated. It is saying instead of using fit generator, you can use model.fit. A light change in the code. That is also fine. I'm running it for 10 epochs. Save the model, run it for 2 more epochs or 1 more epoch. But I already have executed outside for 30 epochs. Outside, that means before coming to this class, I have executed the model for 30 epochs. I have stored it on the GitHub. That means in the classroom, if you execute for 30 epochs, it may take half an hour. There's no point in waiting for half an hour. So what I'll do is I'll stop this process right now. Okay. What I'll do is directly I will take this model. All of you look at this. Directly I'm taking the model here. Okay. And then loading those weights. Where am I loading these weights? From the previously built model. I have loaded this malaria detection 30 epochs. So I'm downloading it, loading it. On top of it, I have run 1 epoch. Effectively at the end of this, how many epochs you have executed if you have taken this data and executed 1 more epoch on top of it? Effectively, how much that will count? If you're starting from here, load dot weights. Effectively, it will
31.
count as 31 epoch. That is the reason why with simple 1 epoch also we have test accuracy 94%, training accuracy 96%. With 1 epoch, usually it doesn't happen that you have that much accuracy. The reason is we are executing from a different starting point. You can take these extra cell images. These are new cells. Let us suppose somebody comes to that machine, puts his blood drops. Then we should predict whether it is a malaria infected cell or non-infected cell. These are the results. Okay. These are the results. For this image, prediction is this one. For this image, prediction is this one. Like this, 6 images are given. These are the predictions. Instead of taking image names, you can actually draw those images and see what is the result. With a normal verification also it is done, but the idea here is to automate this process, isn't it? Millions and millions of people are there. How can you always verify normally? So how do you automate this process? Prediction is class 1 uninfected, class 1 uninfected, class 0 parasitized, class 0 parasitized, infected, class 0 parasitized. These are the prediction. This is one such application of CNN that we can use in real life. Obviously, your model here is giving you 96% accuracy. Any model is as good as the data that you give. If you give poor data, if you don't even have 27,000 images, if you have just 30 images of infection, 30 images of non-infection, can we expect a model to have almost 96% accuracy? Obviously, one thing we always need to remember, any model is as good as the input data. If your input data is not clean, if your input data has issues, if your input images are not very neat, if they are blurred, then the model may not be very accurate. Here we are getting 94% accuracy because we have fairly good amount of data collected by this National Institute of Health. That is one of the applications of CNN. You can have multiple applications as well. You have to come up with that idea. Then the solution can be done easily using CNN. Maybe you may have a pre-trained model readily available, or you have to take the data, collect the data and build the model.